This is lecture or lab 20, rather. And we're going to talk about random forests today. And this follows the material from lecture 20, also on random forests. So we're going to be working with a particularly famous data set. It's a little bit old now. It's called the spam-based data set. You can get it from several places. Several R packages have it. Particularly, there's library Bayes regression has it. And so I could load up that library. You might need to install it, and I can load up my spam-based data. And so here's my spam-based data. And spam-based data is a data set on, I think about 20 years ago now. It's about whether or not certain emails were spam or not. And so it gives word frequencies. It has a first variable here, which is spam or not. So it's a binary kind of classification problem. We want to classify the emails, which are the rows, as spam or not. And the columns are word frequencies. So sometimes it's remove, the kind of frequency with which remove appears in the email, for example. The frequency make. And we could probably find some more information on this if we say question marks spam base. And this is taken from the UCI machine learning repository, and it tells you about the features here. Is spam, is yes or no. So no is 0, and then it has this different frequencies of words. There's a percentage of the time this appeared in the email, for example. So you can imagine that credit or free might be associated with kind of spam emails. And so we'd like to classify these as these emails as either spam or not. And we can do that with a random forest. Of course, I don't have this installed. We can install the random forest package, which includes the random forest. And the random forest package in R is really just calling a low-level Fortran code to fit the random forest. It was written by Bryman and some other people associated with him who came up with the idea of random forest. So Bryman in the late 90s came up with this idea of random forest and really popularized it, although the idea had been floating around, I think, since the kind of mid-90s. But he's very much credited for the kind of explaining how these things work, why they work, and giving a really nice implementation in Fortran, which this package random forest will use. And if you go fit a random forest in Python, it's going to be using the same at the end of the day. This is basically the same code. It's going to call very likely the same Fortran code under the hood. There's just some glue code calling it. And that's true of many of the methods that we look at, many of the more complicated methods. So we can load up this package, this random forest package, and we can fit our random forest. So RF is a random forest. And I can fit my random forest, and I want to fit is spam on everything else, and my data is spam base. So you notice here I'm not splitting this data, the spam-based data, into a test train split. And the reason I don't need to worry as much about that is because I can get an out-of-bag error estimate. So as we explained in lecture, there's a kind of built-in way that kind of that estimates the test error rate without needing to do a test train validation split or needing necessarily to do a cross-validation at a kind of simple level. To fit my random forest, I can pass it these things. Let me just, before I do that, we can read the help here. So X, there's a formula interface for it, but there's particularly important variables are ntree, which I called B in our lecture. This is the number of trees, the number of base methods to collect together. Mtry is the number of variables to sample at each split. And so they give a kind of some suggestions for classification. They suggest square root of p, where p is the total number of variables, and for regression, they suggest p over 3. So this is every time our random tree, so forest is a collection of these, a random forest, a collection of what you might call random trees. And every time our tree splits, for one of the trees splits, it randomly uses a subset of the features. This is to help to decorrelate the trees. And so we need to choose how many that we choose at each split, and that is mtry. And there's some other arguments we pass here, like class weight priors of classes. We have really imbalanced classes, things like that. For example, node size is the minimum size of terminal nodes. Now, for random forest, what you really want to do is you want to overfit your individual trees. The idea being is for each of the individual trees in the forest, you're really overfitting them. So they have a low bias, but a high variance. And then you deal with the variance by averaging together the trees in some ways, or bagging together the trees. So normally we want node size to be quite small. For classification, it uses 1, and regression uses 5, right? So this really potentially, especially for classification, is really overfitting it. But that's okay, because at the end of the day, we average things out. So we can fit this with our call here. Let's say set 100 trees, and mtry is, well, first let's say how many columns. So we have about 58 variables here. We have about 4,600 emails, about 58 word frequencies that we've collected. So 57, let's say, their suggestions use about square root of 57. And I guess this needs to be an integer, so we should say floor square root of 57. Which should be, well, what does that actually give us here? That should be about 7 or so variables that we're going to choose at each split. Fit our random forest. It's going to give us an error. That's never good. Huh. Well, let's look into that. We might need to convert that into a factor. We'll see. Let's just do a real quick summary on our data. See what's going on. It might not like some of these. Might not like the fact that we have these symbols in here. Yeah, probably doesn't like that. So one way we deal with this, I think it might be complaining about the names. Oops. So one useful function is make.names, which will make names that actually work here. So you can see, hopefully this is going to fix some of our issues. How about this? Let's just try this real quick. Let's see. Okay, so yeah, so it doesn't like some of the names at the end because they include symbols in them, so that's not great, right? So if I look at some of the names, like it doesn't like this $sign, it doesn't like this here. How many are there that are going to give us an issue? So probably all these ones with these symbols in it. Ooh, not going to be great. So let's just real quick rename these. So let's just see. We just want to pull off 58, 57, 56. So 56 should give us to there. We just want to pull off these. That's 45, 6, 7, 8, 50. Okay, so maybe it does go 50. Okay. And let's just rename these. So let's just say error frequency, and then let's paste on, let's just name these things that actually won't cause issues. So let's say semicolon, parentheses, bracket, exclamation, dollar sign, pound sign, and that looks pretty good. We actually don't need 56 there, right? We just need 55, right? Okay. So if I just rename these, let's just test this out real quick. Okay, so yeah, let's just rename them like this. And okay, so that should hopefully solve some of our issues. So that, okay, and then the other issue with our data, this is a good live demonstration, be careful about doing things live, is that our first variable is numeric. So if you look at the type of this, what's the function class? It says it's an integer. We really want to make this a factor. So let's do that. And then, okay, so now this should be a factor, and it has two levels, 0 and 1, which is fine. You could actually set the levels as spam and not spam, but let's just use 0 and 1. Okay, now when you run this, now it works. Okay, so we can get some summary on this. I can print out, oh, whoops, I didn't include all my variables. Let's go back and try this again. Now it's gonna take a little bit longer because it has more variables. Okay, so now we did this correctly. Okay, so now it fits everything. So it tells us our formula is spam as everything else, number of trees, how many things we're trying, which is about 7 or so. Variables each split. It says it's doing classification, that's correct. Number of trees is 100. Just variables each split 7. So it gives us an out-of-bag error rate as 4.48%. Now that's out of the box 4.5%. We didn't do almost any fiddling with this, any fiddling with tuning parameters or anything. That's incredibly good, right? We're getting above a 95% accuracy with basically no no fiddling around with anything. So this is really powerful. You could alternatively fit a kind of classification tree. Let's see if we can do this real quick. If I just out of the box were to use a classification tree, let's fit that. Then if I wanted to, let's just see if I use this classification tree, predict the class, and then if I look at the misclassification rate, you see that the misclassification rate, now this is the training misclassification rate for a classification tree. The training misclassification rate I calculated here is about 10%. Whereas the testing, or an estimate of the generalization error for a random forest, out of the box, no fiddling with tuning parameters or anything funky, is 4.5%. So we have the random forest is just dominating this classification tree. Now, the random forest is going to be harder to interpret, but it just does so much better out of the box. You can, of course, play around with the tuning parameters. The base number of trees it typically fits is 500. And let's just do this for demonstration purposes. Let's fit 500. This will take a second to fit, but we can do it. We sit here and we wait and we wait. My little laptop has to do its calculations. There we go. And so here's my random forest again. It's about the same error rate. You can. There are a lot of nice statistics that our random forest function automatically calculates. So here's some of the elements that my random forest object has. Some of these we know because we pass it to it. Some of them we don't know. One nice thing I can do is I can plot my random forest, and I get a plot that looks like this. So we have two classes, the green class and the red class. So if you look at, here's my confusion matrix it's giving me. And the class error for class 0 is about 3% and about 7.5% for class 1. And so you can see this is class 1 up here. It's about 7.5% asymptotically, and class 0, it's about 3%. And the black line here is the kind of combined overall misclassification. What is this? It's error on the y-axis, and it's number of trees. So as I add more trees and more trees and more trees, you can see that initially I have a high error, but as I add trees and add trees, I'm averaging and reducing the variance of my classifier, and I'm getting a better classifier. So you can see this can give you an estimate that I've seemed to have kind of flattened out here. So 500 trees is about good, whereas if I had to use, 10 trees, you would actually have quite a high error rate, which is effectively, if you use one tree, you effectively are getting something like this misclassification rate for our just classification tree, which is about 10%. And you can see that's somewhere around where we would be if we use kind of a few trees. But if we use a whole bunch of trees in a forest, because it averages or somehow bags together the estimates, it's going to reduce the variance of the classifier, and it's going to do much better. It gives us, of course, the confusion matrix. So here's my confusion matrix. So it gives us a 3% or 7.5% for the two classes. You can get the error rate that is plotted above. So this is just the out-of-bag error rate, which is the estimate, as I said in the lecture, of the testing error rate, and the number of trees increasing. So, for instance, if I plotted this, we're going to get that similar plot we get above, right? So that's how that plot comes about. There's also, the last thing I'll say is there's so-called importance score. So like for a regression, you'd have like a p-value or beta, which would tell you something about importance. You can get an importance score for these features, and you can see it says mean decrease in Gini, right? So it's using the Gini index to measure node impurity. That's how it's deciding how to split for the trees. And we obviously want, what do we want? We want the Gini index to be small, because that's going to say we have a pure node. A high Gini index would mean we have a very impure node. And so it's saying for each of the features, we have 57 or so of these features. If I split on this variable across all trees across all splits and all trees in my forest, how much does the Gini index decrease? That is, how much does the variable help? So I could sort these, for example. I could say RF importance scores. I could order them. Oh, maybe I could just sort. I'll say order them decreasing. Let's say something like that. Maybe I can just sort them. Is sorting them going to be quicker? Well, something like that. So you can see this is now lots of exclamation marks have a high importance score, so they're very important. They tend to be associated, they tend to be predictive. So if you have a lot of exclamation marks, yeah, this is used in spam. So we're talking about money, a lot of dollar signs, remove, free. If there's free a lot in the email, that's telling us something about the likelihood that it's a spam email. Lots of capital runs of full capitals, etc. Money, and you can see other things that tend to be associated with predicting spam or not. So frequencies are kind of are a useful tool when trying to figure out what your random forest is doing. What is it finding important? Okay, so that's a nice little tour of random forests. They're one of the, as we saw, they're one of the really kind of out of the box, really powerful methods, and their implementation gives you a lot of nice statistics without having to do a lot of work and cross-validation and things like that. So we'll stop there for this lab.